Okay, so welcome back to the afternoon session. Just a reminder that if you're interested in giving, presenting a problem with open problem session tomorrow, just get in touch with me either by email or come and talk to me. And we'll have a 5-minute slot to maybe push that a little bit, but not too much. So the afternoon session is going to be Srikanth giving a tutorial on the polynomial method.
Okay, thanks. And thanks to all the organizers for inviting me to give this talk. So I'm going to be talking about the polynomial method. More specifically, the polynomial method in circuit complexity and its applications. So what is the polynomial method? Well, the basic idea is very simple, is that so you have a circuit C. A circuit from a restricted circuit class usually, which you want to analyze, and circuits are nasty objects. They're defined in an inductive way. It's not clear what they're doing, and the way we go about doing it is by approximating these circuits by much simpler objects that we do know how to understand. That we do understand. Okay, so the idea is to approximate C by a simpler object. Right, and polynomials are the method of choice here. So why do we go for polynomials? Well, for one, we know a lot about them. Polynomials have been studied since antiquity, so we know a lot about polynomials, and at the same time they're quite an expressive family of objects, right? So just going back to Ryan's talk yesterday, we saw that any Boolean function can be represented as a multilinear polynomial. So I'm just going to go through that again. Right. The way I'm going to be thinking about Boolean functions is that I'm going to be thinking about Boolean functions as functions from 0, 1 to the n to 0, 1. But for now, let me just look at functions from 0, 1 to the n to some arbitrary field. Okay. Typically, this field will either be the field f2, the field with 2 elements, or the real numbers. Okay. So for most of my talk, I'm going to be restricting myself to these two fields, and we are going to be representing Boolean functions. Functions that map Boolean inputs to outputs from this field as polynomials. Okay, and as Ryan mentioned yesterday, he said that he was working over the basis plus or minus 1, but the same thing is true over 0, 1. Every function of this form, not just a Boolean function, not just a function with output 0 or 1, every function can be represented as a multivariate, multilinear polynomial. Okay, so just to recall, Ryan's proof was pretty explicit. Though it was over minus 1, 1. So let me just do the proof again. It's more or less the same proof. So let's do a very simple example. So let's try n equals 2, for example. Okay, so let me start with some arbitrary 2-variable function, and let me write down its truth table. Okay, so suppose I have 2 variables. I'll call them x1 and x2. And f of x1, x2. So let me start with an arbitrary such function. There are four possible assignments here. Right, and we could have some arbitrary 4 numbers. So let's say half, 2, 4, and 7.5. Okay, so and how do we write this as a multilinear polynomial? Well, we saw already yesterday. So the way we do it is that for each of these inputs, we introduce a specific multilinear term. So for example, if I want my function to evaluate to 7.5 on input 1, 1, then what I want to say is x1 times x2 times the value 7.5. Right. Now this multilinear polynomial is going to evaluate to 7.5 on this input and 0 everywhere else. And similarly, I'll probably say 1 minus x2 times x1 times 4, x1 times, x2 times 1 minus x1 times 2 plus 1 minus x1 times 1 minus x2 times a half, right? And this is a multilinear polynomial representation for this function. Okay, let's just see a couple of more examples. So by the way, can everybody at the back see if I write this way? Okay. All right, let's see a couple of more examples, probably more interesting Boolean functions that we like. So for example, let's do the AND function on n bits. Okay. So this again has a very, very simple multilinear polynomial representation, right? So since I'm working over the 0, 1 basis as opposed to the -1, 1 basis that Ryan was using, here this is just a single monomial, right? Evaluates to 1 when all the inputs are 1 and 0 otherwise. Let's look at another interesting function, the OR function. By the way, I should say that I'm using the 0, 1 basis here for the same reason that Ryan was using the -1, 1 basis yesterday. So for Ryan, he wanted the parity to be a monomial, so -1, 1. Whereas I think of ANDs as monomials, they are simpler objects for the results that I'll be describing, so the 0, 1 basis. But many of the results that I'll be describing, they hold equally true if you replace 0, 1 by any pair of elements from the underlying field. So I could work with 1, 3 or whatever, and most of the results would go through. There would be a few changes here and there, but the theorems are sometimes more transparent when you work out the 0, 1 basis, and hence and that's why I'm using it. Okay, so how do I write the OR as a polynomial? Any guesses? Right, so you would use, I guess, De Morgan's laws, right? You would write it as not right, which when translated in the language of polynomials would say something like this. Okay, great. So that's the AND and the OR, which are both important functions for us. Let's look at another important function, the parity function. Right. Okay. So how do I write this as a multilinear polynomial? Well, in Ryan's basis, it was very easy. Here, it's a little bit more of a bit of a chore to do it. But the point I want to drive home here is that it's very field dependent here. Okay, so if I want to sum the input bits mod 2, it really depends on whether I'm working over f2 or not. Okay, so if I was working over the field f2, this is a very simple polynomial. It's just f2, right? But what if my characteristic is not 2? What if I'm working over f3, for example, or the reals? Okay, so in this case, what I really need to do, the best way to do it is to actually transition to the -1, 1 basis and do what Ryan was doing yesterday. Okay, so I translate these 0, 1 inputs to -1, 1 inputs, right? And how do I do that? It's a very simple transformation. We already saw it yesterday. So you send xi to something like 1 minus 2 times xi. Okay, that transforms your 0, 1 input to a -1, 1 input. So you just take the product of that, right? Yeah, and then you translate back to 0, 1. So it's that's going to be what? Is it 1 plus, 1 minus? 1 minus? Okay, good. Okay. I should stress here that division by 2 makes sense because the characteristic is not equal to 2. Okay, so that's how you represent parity over other bases. Okay, and this is how we'll be dealing with multilinear polynomials. So as we've seen now, every function defined on the hypercube has some multilinear polynomial representation. But as has already been pointed out a bunch of times, this representation is unique. This is not a very difficult fact to prove, so let me prove it because it might be useful for me later. Okay. So what is it that I'm trying to say here? Take a function defined on the hypercube, and again, I'm not just looking at Boolean functions, I'm looking at, say, arbitrary field valued functions. I want to say that it has a unique representation as a multilinear polynomial. Okay, so let's see how to prove that. So for contradiction, assume not. So assume that this has indeed 2 distinct polynomial representations, P and Q. Okay. So what are these polynomials going to look like? Well, they are multilinear polynomials, right? So P of x is going to look like I sum over all subsets. For each subset I have this monomial, right? Yeah, and I'm using this notation of Ryan's from yesterday where he defined x to the I to be, and similarly Q can be represented as a linear combination of some other monomials. Okay. And I want to say that P has to be equal to Q. Well, if P is distinct from Q, consider their difference R right. Well, R is going to be a non-zero polynomial because P and Q are distinct. So it's going to have some non-zero term here. I'm just going to write it this way. So R is going to be a non-zero polynomial, which means one of its coefficients is going to be non-zero. And what I want to say is that R cannot vanish on the hypercube, right? Because what we've assumed is that both P and Q define F. So their difference vanishes at all points of the hypercube. Now in order to derive my contradiction, all I have to say is that R cannot vanish over the hypercube if it's a non-zero polynomial. That contradicts the fact that P and Q both represent the same function. Any questions about this? It's clear? Okay. All right. So how do I say that? Well, here's a simple argument. So consider a minimal, so I'm assuming that R is a non-zero polynomial, so there are at least one of these gamma i's better be non-zero. So consider a minimal such. Okay. And here by minimal I mean minimal with respect to inclusion. So it's an I says that gamma I is non-zero, but for all subsets, strict subsets of I, gamma I is 0. Okay, so consider any such minimal I, and let A be the characteristic vector of I. Right. So A is a 0, 1 input, which is 1 exactly at the locations in I. Okay. So what can I say about R of A? Right. So what can I say? Well, I'm evaluating R at the point where at the point A such that A is non-zero exactly at the locations inside I. So if I look at any monomial xj where j is not contained in I, right, the corresponding monomial evaluates to 0, right? Because I'm taking the product of all the variables in j, and j contains a variable that's not in I. All these variables are set to 0, so every such monomial evaluates to 0, right? On the other hand, take any monomial j where j is strictly contained in I. Well, for all such monomials, by definition, the coefficient is 0. So these monomials don't contribute anything. Okay. So the only monomial that contributes at all is exactly the monomial I. So what that means is that R of A is exactly. Okay. So what we've concluded is that every non-zero multilinear polynomial does not vanish at some point of the hypercube. Okay. Which in other words implies that every function defined in the hypercube has a unique multilinear expansion. So indeed the polynomial representations we've written down here are not just some polynomial representations for these functions, they are the unique polynomial representations for these functions. Okay, is this clear? All right, great. So this proof is actually pretty interesting because it yields another useful fact, and that useful fact is the following. Suppose I start with a function that's not just, suppose I start with a polynomial R that's not just non-zero, but non-zero and of degree at most d. Okay. So I just proved that any non-zero R is non-zero at least some point of the hypercube. But instead now consider an R that's not just non-zero, but non-zero and a polynomial of degree at most d. So these gamma i's are 0 when cardinality I is greater than d. Okay. What can I say for an R like that? Well, this minimal I that I chose here is going to be of cardinality at most d, right? So the point where I found that R was non-zero was a point of Hamming weight at most d, right? So we get something stronger. I just want to write that down, record it, because I'll use it later. Any non-zero polynomial let me say R of x, I should say multilinear here, so let me just add it, multilinear, of degree at most d, yeah, cannot vanish, right, cannot vanish. Well, what I just argued is that it cannot vanish at all points of Hamming weight at most d, but in fact you could say something stronger, cannot vanish on any Hamming ball of radius d, right? Okay, and so just to recall, so what is a Hamming ball? So a Hamming ball, so let me say the Hamming ball of radius d around a point A is all those A prime where the Hamming distance, so the number of places where A and A prime differ, is at most d. Okay, sorry. Yeah, sorry, 1 second. Yeah.
Do you need it to be a Hamming ball? I mean, if I say that the vanishing like 2 to the d plus 1 arbitrary points in the hypercube, is that still true?
No, not 2 to the d plus 1 points. You can say that if they vanish on more than 2 to the n minus d plus 1 points, then it's 0. But yeah, right. And for arbitrary points, that's probably the best you can say. Yeah.
2 to the n minus 2 to the n minus d.
Sorry?
How many points?
2 to the n minus d plus 1. Right. So because a non-zero polynomial of degree d is non-zero or at least a 1 over 2 to the d fraction of the hypercube. So
right,
yeah.
So it has to. Okay.
Right.
Yeah,
to the n minus, maybe there's some to the n minus to the n minus d. Okay, sorry. Yeah, there's something there. Yeah, something related to the n minus d. But okay, all right. So right. So what I want to argue is that what we just proved was that a non-zero polynomial of degree d in fact cannot vanish at all of a Hamming ball of radius d. Okay, we just argued about inputs of Hamming weight at most d, which is the Hamming ball around the all zeros point. But if I wanted to argue about some other Hamming ball, let's say I wanted to argue about the Hamming ball around the all ones point, then I would just take my polynomial R of x and transform it to, I'd look instead at the polynomial R of 1 minus, yeah, let's call this R prime of x. Okay. And now R prime of x is a non-zero polynomial because R is non-zero somewhere, R prime is non-zero somewhere. It's of degree at most d because I'm just making a linear substitution of variables. And being a non-zero polynomial of degree at most d means that it does not vanish at some input of Hamming weight at most d. In particular, that input of Hamming weight at most d for R prime is a point in the Hamming ball of radius d around the all ones vector for R. Okay. So just by kind of moving the polynomial all over the place, you can find lots of non-zero points. Okay. So this is kind of confusing. All right. Okay. So good. Right. So polynomials are interesting objects. They are expressive objects, and so we're going to be representing Boolean functions by polynomials. And our interest will be in representing Boolean functions as efficiently as possible by polynomials. Okay. So what do I mean by efficient when I'm talking about polynomials? Well, there are going to be two measures of complexity that are going to be useful to us. There could be many others, but I'm just going to talk about two. I'm going to talk about the degree of a polynomial. Right? Let's say R of x. The degree of R is an important notion of efficiency. Another one that's important is the sparsity of R, right, which is the number of monomials in R. Okay, right. So just stare at these polynomials for a second. The AND polynomial, for example, has degree n, which is as large as can be, right? So multilinear polynomial can have degree at most n, but its sparsity is only 1, it's just one monomial occurring there. So this is degree n, sparsity 1. Okay. The OR polynomial, again, OR is a very simple function. Its degree is again n, because x1 to xn appears in this expansion, and its sparsity in fact is probably 2 to the n minus 1, almost everything. Okay. The parity polynomial, well, it's something similar. The degree is again n, and I guess the sparsity is again 2 to the n minus 1. Okay. Right. So these are important notions of complexity to us. And what we'll be doing is representing Boolean functions as polynomials and looking at these notions of complexity. The simpler the polynomial, hopefully the simpler the Boolean function, etc. Okay. So I should say that the degree is a very nice, robust notion. Robust in the sense that it doesn't really matter if I represent true, false as 0, 1 or minus 1, 1 or a, b. The sparsity, on the other hand, is not a very nice notion, right? Because I can change from the minus 1, 1 notation to the 0, 1 notation, and the sparsity blows up. Okay. So sparsity is not as nice a notion as degree. But at the same time, because it's not so nice, it's kind of, it can have intriguing repercussions. You might get sparse polynomials when you don't expect them. Changing bases might help. So that's also an interesting thing to look at. Okay. So usually, at least for today, the way we'll be bounding sparsity is by saying this polynomial has low degree and hence its sparsity is small. So in very simple ways. Okay, good. Right. So back to polynomials. So we want to represent Boolean functions by polynomials, low degree, low sparsity. But the not so nice thing about this kind of exact representation is that such concise representations of this form are hard to come by. Okay. So for example, we've seen already the AND function. The AND function is a very simple function for us, but its degree is as large as possible. So it's very complicated if I just look at the degree. Okay. The OR function is a very simple function for us, but it's extremely high degree and also not sparse, very dense. Right. So if I look at these notions of complexity and I want to represent Boolean functions exactly, I'm not really going to get very far because ANDs and ORs already become very complicated. Okay. So I also want to tweak my model a little bit so that these kinds of functions, which I think of as simple, have small complexity measures where those are my notions of complexity. Okay. So as a result, I'm going to transition from representing Boolean functions exactly as polynomials to representing them approximately in some nice sense. Okay. So this is the main kind of focus for the rest of the talk, and we'll be talking about notions of polynomial approximations. Okay, so I'm going to be approximating the Boolean function by polynomials of some kind. Right. So what kind of approximations will I be dealing with? Well, there are many different kinds of approximations in the literature. So I'm going to maybe survey a couple. I might use a couple, let me survey one more. So here's the most important notion of approximation for us. So I'll say that a polynomial p, so let me just call this an epsilon Hamming approximation. Right? And this is an important enough notion that I'm going to skip Hamming. So I might just say epsilon approximation. Okay. An epsilon Hamming approximation or an epsilon approximation to a Boolean function is a polynomial. So let me fix a Boolean function f for all of these definitions and some polynomial, let's say r of x. And I'll say that r is an epsilon Hamming approximation to f if the most natural thing happens. So the probability on a uniformly random input that r of x differs from f of x is at most epsilon. Okay, that's an epsilon Hamming approximation. Okay, so here the polynomial is essentially given, the polynomial is essentially penalized for every input where it differs from the original function. It doesn't matter by how much. Okay, there are also other notions of approximation which which are relevant in circuit complexity and other places. So there is where you actually look at how much the polynomial differs from the value of the function. So let me talk about L2 approximations, and these are very closely related to what Ryan was talking about yesterday. So here I'm working over the real numbers, and I say that the polynomial R of x epsilon approximates f of x in L2 if something else happens, and that something is okay. So here I'm actually looking at how much the polynomial differs from the function, and I penalize it for the amount of difference, right? Okay, great. And so let me also mention one other. This is a very important notion in circuit complexity, but I'm not going to get any time to go into it. Notion of a sign approximation. Okay. So a polynomial piece sign represents a Boolean function f if the so here I just require the sign of R of x to be equal to f of x. So let me say to be equal to f of x. Okay. So if f of x is true, for example, I might require the sign to be -1. If f of x is false, I might require the sign to be +1. Okay. So here I'm not allowed to get the Boolean function wrong, so to speak, on any input. I always have to get the sign right, but I never have to get the value right. So I can be anywhere in an infinite interval.
So there's no epsilon. You're not looking at the probability.
Right. I'm not looking at the probability at all. So this is in some sense error free. Okay.
Yeah, can you reduce this to 0, 1, or?
Can I reduce? Can I take a polynomial like this and make it a 0, 1 thing, a 0, 1 valued polynomial? I could, but the degree would probably blow up. So for example, the majority function has a sign representation of degree 1, sign approximation of degree 1, but if you want to write it as a polynomial, probably has degree close to n.
Is there a reason why you don't consider errors in this?
So I could consider errors as well, right? So you can mix and match and do many things. People have considered errors as well. Any other questions? Okay, good. All right. So these are nice notions of approximation. And again, the reason we are looking at approximations is we want more concise representations of our Boolean functions. Okay, and let's see why these approximations can help in this respect. Clearly, we are only helping ourselves by allowing the polynomial to err in a few places. So when polynomials are allowed to make mistakes, then we might get lower degree polynomials, sparser polynomials, etc. Okay, so let's actually look at explicit examples where that happens. So for example, for these functions, let's figure out approximations. Okay, and for now, let me just stick to the first notion of approximation, which is going to be the most relevant for us. So I'm going to try to construct polynomials which are equal to the Boolean function almost everywhere, but are allowed to take arbitrary values at other places. Okay. So let's do it for each of these polynomials. So for example, the AND polynomial, the AND Boolean function. Right. Now if I want to represent this exactly, I need degree n, right? But if I want to represent it approximately, my life is much easier. Because what's the AND function? It's 0 almost everywhere, right? And it's 1 at only one position, at only one place. So I can just approximate it. Let me represent that with this twiddle by the 0 polynomial. Okay. So as long as the error epsilon that I have is larger than 1 over 2 to the n, the 0 polynomial is a good approximation for the AND function. So in some sense, it's very trivial. So I went from degree n to degree 0. Okay. Similarly, for the OR function, I can approximate it by the 1 polynomial. That's again trivial. What about the parity function? Okay. So anybody who does not know the answer wants to guess? Yeah. Conditioned on not knowing the answer, please guess. Well. So the answer is that it can be approximated by a degree square root n polynomial. Okay. So why is that? Well, just for the sake of what I'm going to be saying, just for now, let me assume that I'm working over the real numbers. Okay, but what I'm saying is actually true over any field. But let's work over the real numbers. So what do we know about the parity function? Well, we know that it's a symmetric function, right? It's 1 when the number of ones is odd, and 0 if the number of ones is even. So it's a symmetric function. So let me kind of draw the graph of parity, right? So it only depends on the Hamming weight of its input. So let me say parity of A only depends on the Hamming weight of A. Okay. So I start at Hamming weight 0, Hamming weight 1, Hamming weight 2, Hamming weight n. Okay. And how does parity go? Well, it starts at 0, goes to 1, goes to 0, etc. Okay. All right, great.
What is the epsilon of the approximation that you want?
Ah, fantastic. So let's take epsilon to be a small constant. Thanks. Let's say epsilon equals 0.1. Right. If epsilon becomes less than 1 over 2 to the n, then it's the same thing. So the value of epsilon is important. Let's take epsilon to be a small constant. All right. So this is what parity looks like. Okay. And if I want to get it right everywhere, just intuitively, you have this. You more or less have to do a univariate polynomial, right? So you have, because you only depend on the Hamming weight of the input, you want kind of a univariate polynomial of the Hamming weight that vanishes at 0, takes value 1 at 1, vanishes at 2, etc. So this looks like a polynomial that should have lots of roots, n roots in fact, and you should require degree n, right? But now if you don't have to get it right everywhere, you could just take a few of these points and get it right there, and then you need a lower degree polynomial. Right. And the important observation here is that most of the Hamming cube lies in a very small fraction of this space. So if I look at the space of all Hamming weights, that's a very spread out space, but most of the inputs of the Hamming cube have Hamming weight in a much smaller range than this, right? So just to make things precise, so most of the, let's say 90% of the mass of the Hamming cube, let me change this picture a little bit. So I have this polynomial, right? And most 90% of the mass of the Hamming cube, say, lies between something like Hamming weight n by 2 minus 10 square root n and n by 2 plus 10 square root n. Okay, I'm being very generous here. It's actually much better than that. But most of the Hamming cube actually lies in this range. Most inputs have Hamming weights in this range, right? So if I want to just get it right on most inputs, I might as well concentrate on these Hamming weights and just forget about the rest, right? So what we do is just we interpolate a univariate polynomial that looks like this, right? Yeah. So it's going to get the value of parity right exactly at the Hamming weights in this range, etc. Right? So let's call, and outside it will do something else. Let's call this univariate polynomial u of a single variable, let's call it y. Okay, and the approximation to parity that we get is that, so this is epsilon close to the univariate polynomial evaluated at the sum of the input bits. Okay, yes?
Does it mean that any symmetric function you can basically?
Absolutely. So this argument used nothing but parity. This is true for any symmetric function.
Sorry, I didn't understand what is this approximated epsilon to union of?
Right, sorry, this is not a union. This is the univariate polynomial u. Sorry. Yeah. Okay, so I just take the univariate polynomial, I plug in the Hamming weight, which is just the sum of the input bits, and I'm done. Okay, so instead of requiring a polynomial of degree n, I can make do with a polynomial of degree square root n. Okay. Yeah, any questions about this at all? All right. Okay, so now let's see a kind of application of this notion. Right. Okay, yeah. So what I want to do is now actually use this in order to prove certain interesting results. And my plan for the rest of the talk, if I can get through it, is to prove the most classical result along using this notion, which is a circuit lower bound for constant depth circuits computing the majority function. Okay, so the plan of attack in general is to start with a small circuit, a constant depth circuit. So I'm going to be just looking at AC0 circuits and show that any AC0 circuit is approximated by a low degree polynomial. Okay. By contrast, we will show that the majority function cannot be approximated by a low degree polynomial, and hence we'll conclude our lower bound. Okay. So in order to do that though, it will help to note that this notion of approximation is not exactly what we should be shooting for. Okay. So what do I mean by that? Let me just explain. So this notion of epsilon approximation is useful in the sense that it is sometimes much more concise than the exact representation, but it's not useful when thinking algorithmically, right? So we want to think of this as an algorithm. We want to think of a polynomial as an algorithm, a low degree polynomial as an efficient algorithm. Well, if I think of a low degree polynomial that errs at a few inputs according to the uniform distribution, that's not a good notion of an algorithm. Okay, so why is that? Well, so epsilon approximations are kind of hard to deal with. Okay, and what do I mean by that? Well, one of the things that I would really like to do with an efficient algorithm is that I would like to be able to compose efficient algorithms. Okay, so if I have an efficient algorithm for task A and an efficient algorithm for task B, I would like to get an efficient algorithm for the composed tasks A of B or B of A, what have you. Okay, so it turns out that this is not really, it's not clear how to do that in this model, and that's why this is not very good. What do I mean by that? So suppose I have two Boolean functions, let's say f of x1 to xn and g of y1 to ym, and let's assume that f has, let me write it down here, an epsilon approximation, let's say p of degree d1, and g has an epsilon approximation q of degree d2. Right. I would like an epsilon approximation or something like an epsilon approximation for their composition. Well, what do I mean by their composition? I mean the following function. So let's say f of y1 to ym is maybe little f of, well, okay, this is not a very good, so let me work with many Boolean functions, now just one. So let's say g1 through gn of y1 to ym, and let's say gi has epsilon approximations qi. Okay, and what I'd like is to work with the composed function f of g1 of y through gn of y. Okay, and I would like to be able to show that this has a small degree epsilon approximation, and this seems completely unclear, right? Because okay, on a random input I can replace gi by qi without a loss, right? But now what about f, right? The distribution that's feeding into f from the gi's is not necessarily the uniform distribution, right? So if I only have an approximation of f with respect to the uniform distribution, I cannot really replace it by its approximation with respect to that distribution and hope that it works with respect to this other distribution, whatever I'm getting here, right? So this notion of epsilon approximation is all good for proving lower bounds, but for the purpose of proving upper bounds, it's not really great, right? It's the same reason that distributional algorithms are kind of hard to work with, right? You have an algorithm that works with respect to a certain distribution, then you have to be really careful that your input's actually coming from that distribution to be able to use it. Okay, so though we are going to use this finally to prove lower bounds. Yes?
Particularly you can think of f and g as the end and O, and then if you approximate it by constant, you get nothing.
Right, absolutely. So yeah, right, it shouldn't be the case that, right, so for ands of ors, you probably need large degree to approximate their composition, but each of them has a constant approximation, right? So right, so what you want is a notion of algorithm that you can actually compose, right? So instead of dealing with distributional algorithms, the kind of thing we have here, we deal instead with randomized algorithms, right? So randomized algorithms is something we all know very well. They're algorithms that use a little bit of randomness but nevertheless work on every input, and this is a notion that we can actually compose. Okay, so the notion of polynomial approximation that we will finally use in order to approximate a circuit class is the following thing. So I'll call this a probabilistic polynomial. This is the standard notation. and let me say PP for short. Okay, so now my algorithm is not a single polynomial but a distribution over polynomials. Okay, so it's mu, a distribution over polynomials, right? And I say that it has degree at most d if the distribution is over polynomials of degree at most d. That's it. Okay, so I now say that let's say mu is a delta error probabilistic polynomial for f, right, if the probability that p of x, so p is a random polynomial drawn from the distribution, p of x equals f of x is at least 1 minus delta. Okay, and here the important thing to note is that this holds on the worst case with respect to inputs. So for all x in 0 1 to the n, this is true with probability at least 1 minus delta. The error is only with respect to the randomness in the algorithm, which is the sampling procedure required to sample from u. Okay, yes, any questions? Sorry?
Do you assume that it's efficiently sampleable?
Do I assume that it's efficiently sampleable? I don't make that assumption while defining it. I don't think I'll need it, so yeah, no, right. And any other question? Maybe I will, yeah. So it will be clear. I will be using it in a specific context and then probably be clear, yeah. Any other questions? Okay. All right. So the nice feature of this definition is that now we have a randomized algorithm, a real randomized algorithm, so we can compose. Right, so let's say features. Well, the first thing is the following. So suppose now we are back in this setting here. Yes?
I've got a question about the polynomials themselves. Before, like you said that at the beginning that the goal was to get like simple polynomials.
Right.
Here, so for a single one, it was kind of easy to define.
Right.
Here, like, is it also like for mu is supported, will be supported on simple polynomials?
So mu is going to be supported only on degree d polynomials. So if I say a probabilistic polynomial of degree d, mu is going to be supported on polynomials of degree d. That's how it would work. Yeah, that's a good question. Anything else? Okay. So what are the features of this definition? Well, a couple of nice features. Well, one nice feature and another notable feature. Well, the first feature is that it's composable. Okay. So what do I mean by that? Well, let's go back to this setting here, and instead of epsilon approximations, say we now have epsilon error probabilistic polynomials. Let's say PP, and let me just say epsilon PP, and you'll know what I mean. Epsilon error probabilistic polynomials. Okay, so now I have epsilon error probabilistic polynomials for f and each of the GIs. It should be easy to see that the composed polynomial, which is p of q1 to qn, is a delta PP for capital F, where delta is whatever I get by just using the union bound. So epsilon times n plus 1, I guess. Right? So on, right, I should say that this probabilistic polynomial is I sample q1, I sample q2 independent of q1, I sample q3 independent of q1 and q2. So these polynomials are all sampled independently of each other, and then I just compose them. Say that's the simplest way of doing it. Let's just do that. And the probability that any one of them makes an error is at most epsilon times n plus 1 on any input, right? And hence this an epsilon times n plus 1 error probabilistic polynomial. Okay, so composition is an important one, so and we have it. The second thing is that I can, from this notion, I can always pull out an epsilon approximation in the previous sense, right? So now suppose I have an epsilon error probabilistic polynomial. So okay. So I hope this was completely clear. Yeah.
So like if you sample them independently, should it be like epsilon plus 1 minus?
You're right. I'm just kind of upper bounding the error. Just something right. It will probably be a little bit better than that, right?
Yeah, sorry. So both the p and the q's are epsilon polynomials in that statement?
Right. So these are p and the qi's are epsilon error probabilistic polynomials. So I should really think of them as randomized polynomials. So I'm using some bunch of random bits in order to sample p and q1 to qi.
Yeah, I'm just making sure that both are epsilon because you just have one parameter.
Right. Yeah. They're both epsilon.
P and q are different.
Right. If they're different, then you'd have to add up the right errors. Right. Yeah. Okay. All right. Great. And so now, and also this relates to our previous notion of approximation in the sense that if I have an epsilon probabilistic polynomial p, right, now p is a random variable, it's a randomized algorithm. From here I can always get a single polynomial which is an epsilon approximation to my original function, right. So if I have an epsilon error probabilistic polynomial p for f, right, I should really be representing p in bold font. If I could, I would. So let's say p. Right, it's a random variable. From here I can always get an epsilon approximation p for f, right, because now when I'm choosing inputs uniformly, at every input most of my samples are good, so there's going to be one sample, one polynomial in the support of my distribution that is good for at least a 1 minus epsilon fraction of inputs, right. So by an averaging argument I can always get a single polynomial p that's an epsilon approximation for f. Okay, and I should stress here that this has nothing to do with the uniform distribution. I could have any distribution over my inputs. I would always be able to, by averaging, get a single polynomial that works for most of that distribution. Okay, and this really tells you why the notion of probabilistic polynomial is a little stronger than the notion of normal epsilon approximation, because what you're really getting is an algorithm that works with respect to any distribution, or different algorithms depending on the distribution, but you get algorithms with respect to every distribution. So really you're doing something stronger. Okay, but unfortunately we need to deal with this in order to get the circuit low bound. Yeah, question?
Are these guys truly duals in like the sort of
right, if you want to get it right with respect to every distribution, you need a probabilistic polynomial, right. So this is just LP duality, absolutely. Okay, great. So now that I've actually defined the notion of polynomial approximation that we will use, let me prove a theorem regarding the power of these approximations, which is useful in proving the lower bound. So maybe I'll prove this theorem first, we'll go for a break and then come back and see the lower bound. Okay, so what's the theorem? This theorem is due to Rasbora. Okay. And the theorem states that any AC0 circuit C of size S and depth D has an epsilon approximation, I should say epsilon probabilistic polynomial of degree something like log s to the d minus 1 times log 1 over epsilon. Okay, so I should say that this result is over the field F2. Okay, so we haven't really constructed any probabilistic polynomials yet, and we are going to construct probabilistic polynomials for ands and ors. And by composition, what we are going to get is this theorem of Rasbora, which says that any circuit in AC0, any AC0 circuit of small enough size has an epsilon probabilistic polynomial of not very large degree. Right? Typically, you should think of this size as polynomial in the number of variables, in which case this epsilon is some sort of constant. Okay, in which case this would be a polynomial of degree polylog n. Right? So just to contrast with the actual degree of ands and ors are both if you want to represent them exactly, you need polynomials of degree n, but if you want to approximate them in this very strong sense, you only need degree polylog n. Any questions about the statement of this theorem?
Was that log 1 over epsilon side the exponent?
It's outside, right? So it's this times this, yeah. Okay, great. All right, so let's do it. Okay, so how do we prove this theorem? As I said already, the way we are going to do it is we are going to use the fact that we can compose these polynomials together, right? And so we just need to do it for the constituent elements of our circuit, right? We're going to compose things d times, so our degree will get blown up by a power of d, but that's not much, d is a constant. So all we need to see is that every single AND and OR gate can be represented as a polynomial of degree, well, something like log s, and then we are done. Okay. So let's see how to do this, right? So a basic observation, let me just say this for the sake of completeness, is that a NOT gate, so usually we think of, as Ben mentioned yesterday, we think of the literals as lying just above the variables here. I'm sorry, the NOT gates as just being just above the variables here. So we actually do have NOT gates as well, but NOT gates are never a problem, because if I have the NOT of a single bit, let's say xi, I can represent it exactly as a polynomial of degree 1. Right, so there's no error here, and I only have degree 1, which is as small as I can go, so this is great. So for NOT we just do this, right? It's only the ANDs and ORs that we actually need to do something, and among the ANDs and the ORs we just need to do something for one of them, okay, because they're dual to each other, right? Again, going back to De Morgan's laws, we're going to use the fact that AND of x1 to xn is 1 minus OR of 1 minus x1 to 1 minus xn. Right, and now if this had a probabilistic polynomial of degree d, these guys have 0 error probabilistic polynomials of degree 1, so the entire thing is a probabilistic polynomial of degree d. Okay, so we just need to do OR, right? And OR, it turns out, is not very difficult, right? So how many variables am I going to have in my OR in general? Well, I'm looking at a general OR in my circuit. My circuit is this. I have an OR gate somewhere. I'm looking at the inputs feeding into this OR gate, and it's a circuit of size s, so there are going to be at most s inputs, right? So let's assume that there are s inputs. Okay, so OR of x1 to xs. Yeah, and how do I do this? Well, so I want a randomized algorithm. Okay, so now is the real trick. I want a randomized algorithm. It's a randomized polynomial, such that whenever the OR is 0, this polynomial is with high probability 0. Whenever the OR is 1, that is on any non-zero input, this polynomial is with high probability 1, right? So let's start with instead of a high probability algorithm, let's start with a algorithm that just has some reasonable probability of success, and then we'll amplify, right? So what's a simple polynomial that has a reasonable probability of success? Here's one. So choose a y randomly from f2 to the n, f2 to the s actually, which is 0, 1 to the s, right? And I have a probabilistic polynomial py. It's a polynomial that depends on y, probabilistic polynomial of x, which is just the sum of xi times yi, right? So it's just the inner product between the vectors x and y. Okay. So what property does this polynomial have? Well, surely if my input was 0, which is the only 0 input for the OR function, this polynomial is always 0. How much time do I have?
5 minutes.
5 minutes. Right, it's always 0. On the other hand, if my input is 1, okay, so I have a non-zero input and I take its inner product with a random vector. What's the probability that this is 0, right? And what's the probability that this is 1? It turns out the probability that this is 1 is exactly a half. Okay, it's exactly a half, but what's relevant to us is that this is at least half. All right, so you have a probabilistic polynomial here of degree 1. Okay, right, this is a polynomial of degree 1. The degree in the randomness does not count, does not matter. It looks like a polynomial of degree 2, but it's actually a polynomial of degree 1. It's a probabilistic polynomial of degree 1, which is kind of a one-sided error algorithm for OR. If the OR is 0, it's always 0. If the OR is 1, it's 1 with probability at least a half. Okay. The only problem is that this is a polynomial that makes a reasonable amount of error. So what we want to do is reduce the error of this, right? So we have a one-sided error algorithm. We want to reduce the error. So what do? We run it a bunch of times and we take the OR, right? Okay. So reduce error, let's say to epsilon or maybe to delta. You take something like some L invocations of this algorithm. So L vectors y1 to yl and transform them to the polynomial OR of py1 to pil. Okay, so you choose L uniformly random polynomial, L vectors y1 to yl independently and uniformly at random and take their OR. Okay, this seems kind of non-intuitive. You wanted to compute OR and here you want to compute OR again. So what we need to realize is that we wanted to approximate OR on S bits, and here we just have OR of L bits, and L for us is going to be something not very large, log 1 over delta. Okay. So when L is so small, I can actually write down the exact representation for this polynomial. I just take the OR on L bits and I just write it down as a polynomial, expand, and this is going to be a polynomial. So let me write it down explicitly, 1 minus product I, 1 minus pyi. So this is going to be a polynomial of degree order L. Okay, so more or less done, just a couple of minutes and then, okay, good. All right, so right, so is this clear to everybody? This is reasonably clear? Okay, good, right? So what this does is that it gives us a delta error probabilistic polynomial for the OR function of degree L, which is order log 1 over delta. Okay, and then I take this polynomial and I compose it to get a polynomial for the entire circuit. Okay, and that's more or less it. We just one last trick. So which one do I want? I want this one. Okay. So composition. Right? So now I have my circuit. It's got some gate, maybe G1, the gate G2, and the gate G3, right? So maybe a G4. So my circuit kind of looks, if I write it as a composition of functions, it's going to look something like G3 dot 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 G2, inside which there's a G1 dot 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 G4, etc. G stands for gates here. Now I approximate each of these gates by a low degree polynomial. Yes, question?
Just maybe you're going to address it, but then how do you get the log outside the exponent?
Oh, good. Yeah, I'm just going to get to that. So that's the last little trick. I'm just going to get to it. Okay, good. So now I replace these by probabilistic polynomials. So a G3 becomes a polynomial maybe P3, P2, P1, P4, etc. Okay, and overall I get a polynomial P for the circuit. Okay, I'm more or less done. Only I need to ensure that the errors here are small enough so the error overall is small. Okay, so what kind of errors should I choose? So let me choose delta equals something like 1 over 10 times the size of the circuit. Okay, if I choose delta to be 1 over 10 times the size of the circuit, each of these polynomials is going to err with probably 1 over 10 times s. So I get a polynomial P has degree order log s to the d. Okay, right? And P is a 1 over 10 probabilistic polynomial. Okay, all right. So now suppose I want another probabilistic polynomial that errs with probability at most epsilon what I want to do is I have a randomized algorithm that errs with probability 1/10. So I repeat something like log 1 over epsilon times, and I take the majority vote. Okay. So final error reduction. Choose something like P1 to PL. The superscript indicates that they're all copies of the same polynomial P. And here again, L is going to be something like log 1 over epsilon. And the final polynomial Q is going to be the majority. Right? And again, we can write down the majority polynomial because the majority polynomial of very few bits. We just write it down of P1 to Pn. Okay. So that's a polynomial of degree log s to the d times log 1 over epsilon. If you really care about the log s to the d minus 1, you can note that the outermost gate, this G3 here, only needs a probabilistic polynomial of constant error. So you don't really need degree log s for this, so you get it down to. Yeah. Okay, so that concludes the proof of the theorem. Any questions about this? Okay, great. So let me stop here. We can come back after the break and take.
Okay.
Yeah.
Any questions about the first part of this talk? So what's really the parameters that Rasbora got?
Right. So it's not quite Rasbora. So Rasbora, I think normally what happens is that you essentially set the error to epsilon over s inside individual gates, and then you get the epsilons inside. So yeah. So this was stated in this language in a paper of Swastik, Koparty, and myself. But I think it's also implicit in some earlier work of Allenders from back in the mid 80s. Yeah.
Can you improve slightly the dependencies if you have something about like maximum arity of a gate inside, or if you do like some accounting to avoid?
Can you improve the degree here?
Yeah, if I tell you that like most of the time the gates will have smaller arity.
Right. So actually that is true. I mean, in certain situations we can improve it just exactly based on that. For example, if we have a large OR of small circuits, for example, then we don't just say that the entire circuit has that size. We do something better, and this is useful in certain situations. Yes, you can, but in general, this bound is more or less tight.
So actually, similar question. So if you assume that it's a AC0 formula, do you think we can analyze it in a finer way?
I have not tried.
Question for Ben.
Right. So he's the right person to ask. Yeah, I don't know. Very possibly, I'm not sure. Yeah.
Okay, so let's come back in half an hour for the second part. Let's start.